Hi students, in this video I would like to discuss about extended version of Master's theorem. So this is the extended version of Master's theorem. So we already discussed we have three cases in Master's theorem, and in extended Master's theorem, if case 3 of Master's theorem is satisfied, we all know case 3 means f of n part will be larger and f of n equal to theta of n raised log a to the base b dot some log raised to kn. Then we can write t of n as theta of n raised log a to the base b log raised to k plus 1 n for k greater than or equal to 0. So I would like to explain this extended version of Master's theorem using an example. So just look at this example. Here t of n equal to 2t n by 2 plus n log n, where a equal to 2, b equal to 2, n raised to log 2 to the base 2 is n raised to 1, that is n. F of n equal to n log n. We are comparing n and n log n. N is less than n log n, that is n raised log a to the base b is less than f of n. So case 3 is satisfied. If case 3 is satisfied, you have to check one more condition. So can we write f of n in the form n raised log a to the base b dot log raised to kn for some k greater than or equal to 0. What we have to check? We have to check whether we can write f of n in the format n raised log a to the base b dot log raised to kn. K can be 0, k can be 1, etc. Here n can be written as n raised log a to the base b. Here log n can be written as log raised to 1n. So here we can represent f of n in this format for k equal to 1. So if so, what is t of n? T of n is theta of n raised log a to the base b log raised to k plus 1. Since here k is 1, here it will be n log square n. So this is extended version of Master's theorem. Next we are going to see more examples from Master's theorem. Next example is t of n equal to 4t n by 2 plus n, a equal to 4, b equal to 2, log 4 is 2, so it is n square, f of n is n square is greater than n. First case is satisfied, so t of n equal to theta of n square. Next example, t of n equal to 4t n by 2 plus n square, a is 4, b is 2, this n raised log a to the base b is n square, f of n is also n square, both quantities are same, so case 2 is satisfied. So we will write f of n log n. F of n is n square, so it is n square log n. Next example, t of n equal to 4t n by 2 plus n cube. Here a is 4, b is 2, n raised log a to the base b is 2. Here n raised log a to the base b is n square, f of n is n cube. Here case 3 is satisfied. So in the extended version we studied, if case 3 is satisfied, we have to check one more condition. Can we express f of n in the format n raised log a to the base b log raised to k? So here this quantity is n square. F of n itself is n cube. So anyway we can't represent. So we will go for the normal Master's theorem. So it is theta of n cube, since it is case 3. Another example, t of n equal to t n by 2 plus log n. A equal to 1, b equal to 2, log 1 is 0. So it is n raised to 0. F of n is log n raised to 0 is 1. 1 is less than log n. Case 3 is satisfied. Since case 3 is satisfied, I am checking for extended Master's theorem. Here we can represent f of n in n raised log a to the base b log kn. Here f log a to the base b is n raised 0, that is 1. 1 dot log n. Log n can be represented as log raised to 1n. So k equal to 1. If so, what is t of n? Theta of n raised log a to the base b log raised to k plus 1n. So since k is 1, here this quantity is 1, here k is 1, so it is log square n. Remember, log square is nothing but log n. Next example, t of n equal to root t n by 2 plus log n. A equal to root 2, anyway root 2 is 1.41 something, so anyway a is greater than 1, so that condition is satisfied. B equal to 2. Next, n raised to log root 2 to the base 2, that is n raised to 0.5. So if you have any confusion, you just look at right side. So we all know 8 is 2 cube. So log 8 is 3. to the base 2. So root 2 can be written as 2 raised to 1 by 2. So log root 2 to base 2 can be written as 1 by 2. This is how I got 0.5. So f of n equal to log n. N raised to 0.5 is greater than log n. N raised to 0.5 is nothing but root n. We all know root n is greater than log n. So case 1 is satisfied. T of n equal to theta of root n. Next example, T of n equal to 3Tn by 3 plus root n, a equal to 3, b equal to 3, log 3 to the base 3 is 1, so n raised to 1 is n, f of n equal to root n. We are comparing n and root n. N is greater than root n, case 1 is satisfied, so we will write it as theta of n. Next example, T of n equal to 2Tn by 4 plus n raised to 0.51, a is 2, b is 4, n raised to log 2 to base 4 is n raised to 1 by 2, f of n equal to n raised to 0.51. I am comparing f of n and n raised to log a to the base b. Here f of n is greater, so case 3 is satisfied. If case 3 is satisfied, I have to check for extended master's theorem. We can't express f of n in n raised to log a to the base b log kn, so t of n equal to n raised to 0.51. So if anybody have any doubt how I calculated log 2 to base 4, and you just look at this right side. Next example, T of n equal to 16Tn by 4 plus n factorial, a is 16, b is 4, n raised to log 16 to the base 4 is n square, f of n is n factorial. I am comparing n square and n factorial. Anyway, n square is less than n factorial. Case 3 is satisfied. I have to check for extended version. Here also we can't represent f of n in n raised to log a to the base b log raised to kn format. So t of n is n factorial. Next example, t of n equal to 0.5Tn by 4 plus n factorial. Yes, n is 0.5. We already studied a must be greater than 1. Here in this case a is less than 1. So we can't apply Master's theorem here. Next example, T of n equal to 16Tn by 4 minus n log n. So you just recollect the general form. T of n equal to Atn by b plus f of n. Here f of n is negative, so we can't apply Master's theorem. Thank you.